In this video, we're going to learn about the periodic table. So here's the periodic table. It's arranged into rows called periods and columns called groups. The columns, elements in them will have similar chemical properties, even if their physical properties may differ. So let's look at the different zones of the periodic table. On the left side, we've got our metals, and on the right side, we've got nonmetals. The majority of the periodic table is metals, which tend to be solids, the exception being mercury. They're ductile, meaning that they can be drawn into a wire. They're shiny with this metallic luster. They're malleable, which means that they can be hammered into different shapes. And they're very good conductors of electricity and heat. Nonmetals are pretty much the opposite. They might be solids, but they could also be liquids and gases. Many of them are. And they are dull, they're not shiny, they're brittle, meaning that if you hammer them, they'll just break apart, and they are insulators, they are poor conductors of heat and electricity. Now, metalloids, they're kind of in between. They have properties of metals and nonmetals. They tend to look like metals, meaning that they have this shiny luster, but they're they're decent conductors, they're semiconductors, and they are brittle in general. So if you ever have a piece of some metalloid, it looks like a metal, but if you hit it, it will probably just crumble. Want to point out that there is this staircase here that divides the metals from the nonmetals, with the metalloids basically anything touching it. I guess you need to just memorize that aluminum is a metal, which shouldn't be hard. And astatine technically is on the staircase, but it hardly exists. Only a few grams in the universe exist at any given time, so it's not really something we'll be talking about. All right. So if you look as you go to the left of the periodic table, I think it's quite obvious that that's where metallic character is increasing. As you go down the periodic table, it's quite interesting because you'll see an increase in metallic character as you go down. And the example is in the group 15, which, yes, I guess you can see that there are two nonmetals followed by some metalloids, following by the most metallic of the group 5 elements in bismuth. But maybe we should look at them. Nitrogen, being a gas, is about as non-metallic as it gets. Phosphorus, perhaps a little bit less so because it's a solid, but definitely not shiny or anything. Arsenic is starting to look a little bit metallic, but it's a metalloid. Antimony, a bit more metallic, yet if you were to play with it a little bit, you'd find it's really not a good conductor. It's still pretty brittle. Bismuth, though, is full-on a metal. And that's how you can tell, as you go further to the lower and left side of the periodic table, we have more metallic character. And then as we go to the upper right corner, we have non-metallic character increasing. So moving on, there are a few element groups that we need to know a little bit about. In group 1, there are the alkali metals right here. Being very far to the left, they are very metallic, which means that they're very soft. You can actually cut them all with a butter knife. I know that francium doesn't look like a metal, but this picture of francium is not really showing francium. It's showing a rock that contains probably a few francium atoms. Like astatine, francium is something that barely exists in the universe, so it's so radioactive you'll rarely see very much of it, which is why we see it here as essentially just a rock with a few francium atoms. But the others, they look quite metallic, and they are very, very soft. They're reactive because they're very close to that noble gas electron configuration. Metals will lose valence electrons. That's something that they all have in common. They will lose valence electrons, where nonmetals will gain them. Unless, of course, we're talking about the group 8 elements, the noble gases, which don't need to gain any. They have full outermost shells. More on that in a minute. So the outermost electron configuration for any alkali metal is S1. We have lithium. That'll end with 2s1, sodium will end in 3s1, potassium in 4s1, etc., etc. Let's go to the alkaline earth metals now. They are group 2, and they're next to the alkali metals. They are a little bit less metallic. They're going to be a little bit harder and pretty reactive, but a little bit less so. For example, lithium, when put in water, will bubble immediately. Beryllium won't. Magnesium won't really either. Calcium, when you get down to calcium, you finally get reactivity on par with lithium. Um, so they're a bit reactive, still not as much as the corresponding same period alkali metals. And their valence electron configuration ends in s2. So beryllium would be 2s2, et cetera, et cetera. Just looking at these samples, they perhaps look a little bit less metallic than the alkali metals, like magnesium perhaps. As you go down, they look a little bit more metallic, like barium definitely looks a little bit more like a metal, and it definitely behaves like a metal in its other properties aside from its appearance. The D block is next. This is not a group of elements. This is a whole region, and they're called the transition metals. They are less metallic still. They tend to be hard. Obviously, there are exceptions. Mercury is a liquid, for example, but they include things like iron, for example, which is quite hard. You can see some examples over here. The period 4 transition metals. The transition metals tend to be less reactive, which is one of the reasons why they tend to be more useful, and you probably have seen them more. Iron is used to build structures because it's not going to react with things as much. They also include the noble metals like gold and platinum, which are totally inert. Noble metals, think noble gases, are inert elements. Well, gold and platinum are chemically inert as well, so they're called the noble metals. That's why you actually don't need to polish gold or platinum jewelry. Of course, being in different groups, they have a different range of electron configurations. In general, they will lose their s electrons before the d. So if you're trying to figure out what ionic electron configuration titanium has, it will actually, if it forms a +2 ion, it will change from s2d2 to being just d2. The s electrons are what are lost first. They also tend to have a D5 or a D10 electron configuration when possible. And an example here is chromium. You would expect that it would be S2D4, but it's actually 4S1, 3D5. One of the S electrons gets promoted into a D, and that's just because with the S, it's going to have one electron, and there are 5 d orbitals. Notice that we don't have electron-electron repulsion within the shells. It's kind of like Hund's rule, and that's seemingly a violation of the Aufbau principle because the d is a little bit higher than the s, but they're so close together that it's not a big deal to promote one of the s electrons from being, s2 into an otherwise empty d orbital. The loss of repulsion by having 2 electrons in the s orbital actually is going to be more than canceling out the gain in energy of putting an electron into the d. Additionally, we have copper, which is going to be 4s1, 3d10 rather than 4s2, 3d9. It looks like it should be d9, but it's d10 for similar reasons. The minimizing of repulsion in the s shell is favorable. And of course, zinc will be d10 as well, but it has an extra electron, so it will be 4s2, 3d10. Moving on, we've got the halogens, which are very, very, very much non-metallic. They're group 7. They easily gain a valence electron, so they are quite reactive. They're one away from having the electron configuration of a noble gas. They include gases, a liquid, and a solid. What you can see here is chlorine gas. Fluorine isn't even here because it is so reactive. It will actually start to slowly corrode glass, so it's hard to really get a photo of it safely. So fluorine is not here, but this is chlorine gas. Bromine is a liquid, but it is quite volatile. You can see gaseous, the sort of reddish brown gas of bromine that is above the surface of the liquid. Then finally, we have iodine, which is a solid at room temperature, but it actually will sublime. And so, especially even a tiny amount of heat, if you warm it up slightly, well below the point of sublimation, it will have quite a bit of this purplish gas of iodine above it. Last but not least, we have the noble gases, which are all gases. They all have full outermost S and P subshells, meaning that they have 8 valence electrons, and that will make them chemically inert. They are right over here, the far right, and you probably are familiar with helium being that gas used in balloons. Neon, you may have heard of neon lights. Well, neon lights, I guess neon was the first, and yeah, you'll get this bright red light, but actually other so-called neon lights are not with neon, they're with other elements in them. If you want a nice purple color, try using argon. Xenon you may be familiar with as in a lot of car headlights because they can be pretty bright and they're not particularly colorful, they're a little bit purple. But every one of the noble gases in a discharge tube will give you a different color. And that's something for discussion in the context of actually electron configurations and electron energy and light. Anyway, this is a nice introduction to all of the important groups of the periodic table, several of the groups of the periodic table, and the organization of the periodic table. So let me know if you have any feedback or questions in the comment section below. Thanks for watching.